Okay. So welcome back to the last hour for today. And as I said, maybe the first 15 minutes we will spend still with the Falkner scan profiles, and then we will move on to the transition and stability topic. Yeah, but what we wanted to do, or the last thing that is open for Falkner scan, is actually to look at the equation, the transformed boundary layer equation, and then how to calculate profiles. And what we just said before the break is that we have now this equation, or this definition of our non-dimensional variable eta as c times y times x to the a. That's our starting point. And what we need to calculate here is the c. And as I said before, we know the c for Blasius. So if a is 0, if a is minus 1/2, then we know what c should be. It's this. It's the square root of u infinity and eta and mu. So that means somehow we need to choose this c, and the idea is that we choose it, or choose c, such that we recover Blasius for, well, m equals 0 or a being minus 1/2. So we would like to get our C in such a way that it actually becomes consistent, so that our picture is kind of a consistent picture. Well, okay, so how can we now do that? Well, we have derived before our, well, so we have the G2 of eta, and we have the G3 of eta. G1 is 0, so we don't need to care about G1. So it's just G2 and G3. And what we have done before was we said that that G2 is this UE times A divided by mu c squared x to the 2a plus 1. This we knew from before. But now with our additional variables that for the additional things that we introduced on the way, namely we have replaced UE as being k times x to the n. There was one equation that we introduced. So we have k times x to the n times a, and then down here we have the c squared and the x. We cannot really do anything more here, so it's just mu times c squared x to the 2a plus 1. And if I just make this a little bit nicer, I get 2 mu c squared down here and k to the n plus m minus 1. And this happens because the x to the m and the x to the m, of course, disappears, has to disappear. That was the whole point. But this is now the result for G2. And for G3, I can do the same thing. I just write in everything I know. So this was the original definition, where we have mu c squared x to the 2a. And if I again introduce the case that I have from before, I get k to m x to the n minus 1 here, and down here I get mu c squared x to the n minus 1. Of course, also here, the x to the n minus 1 will disappear, as it has to. And what we get at the end is k times m divided by mu c squared. So this is G2 and G3. Now, again, what is open here is the value, or how to define C. That's still what we're kind of looking for. We would like to find a good way of defining C such that we recover Blasius in the case when n is 0. There's of course various ways of doing that. There's not just one way, but one specific way that we can do that. We can essentially say that G3 minus G2 needs to be 1/2. Why? Well, if we go back to Blasius and we subtract G3 from G2, we actually get 1/2. So that's the reason So this would then be exactly this way that is consistent with Blasius. So that means if we manage to set the C in such a way that G2 and G3 have this relation with each other, then we have obtained our, the goal of being consistent. So if we do that, now in our case, we get Km divided by nu C squared, that's G3, minus G2, which is Km minus 1 divided by 2 nu C squared. This should be 1/2. Of course, now you see that we can directly eliminate C or extract or isolate C. So we get C squared being K1 plus M divided by nu. So this is our value for C, which is then consistent with Blasius. And if I'm now taking this one, if I'm taking this C and I'm plugging it into my my eta formulation, or the formulation for eta, what I will get is eta is y times the square root of n plus 1 times ue of x divided by mu x. So I just take my definition of C that I have here, I plug it in here, and I replace again x to the a with essentially with ue, which I can do. And of course, now we can ask ourselves, well, did we obtain this consistency with Blasius? Well, if m is 0, then I get here, of course, 1. So the square root is only ue, which then for Blasius becomes u infinity, divided by nu and x. And that's exactly what we had for Blasius. So that means this the definition of eta in this way is exactly consistent with Blasius for m being 0. And if m is non-zero, then we get a slightly more or less stretched version of this. Okay. So this is now our similarity variable. And now if you think back what we did with Blasius, we were essentially introducing this eta into the boundary layer equations. And if you remember back, there was a lot of chain rules and so on for replacing all the derivatives in such a way that that we introduce this eta. Of course, that's essentially the same way what we now had to do as well. Of course, most of the work was already done because we have already extracted G2 and G3. But still now with this result, we had to put everything back. And the final result after some calculations, a few pages of calculations, you would then get that the final similarity, the similarity equation, and that is now what is called the Faulkner scan equations, are the following: f 3 primes plus 1/2 f double prime plus beta h divided by 2 1 minus f prime squared is 0. So these are the equations that you would get if you introduce this eta into the boundary layer equations. And of course now we actually see quite easily that we have obtained our goal with the consistency with Blasius, because it turns out that the first two terms, these guys, are exactly the Blasius terms. So this is the Blasius equation. And it's only, so the Faulkner scan bit is only this beta h divided by 2 times 1 minus f prime squared. And of course, the cool thing now is, if we have 0 pressure gradient, then it means that this beta is actually 0. So that means in the case of a flat plate, in the case of a flat plate, this term is gone. So that means then we recover Blasius, as we should. So that means this term, the Faulkner-Scan term, that is an additional term due to the pressure gradient. And it only appears if there is a pressure gradient. Otherwise, it would be zero. I guess now you also see the beauty of the way that we have derived now the Faulkner-Scan equations. It really connects nicely to Blasius, and it's essentially just an extension of Blasius, or a generality, or a generalization of Blasius, in the sense that you allow the free stream velocity to vary as a power law. Not just constant, which is power 0, but you allow it as a power law x to the n. And in any of these cases, you will get a similarity solution. So that's the kind of how should I say, the result of Faulkner-Scan, or the idea of Faulkner-Scan. For completeness, I should also mention what the boundary conditions here are. These are as before. It's actually the same as for Blasius. F for 0 and f prime of 0 is 0. And then we have the free stream boundary condition as well, which is f prime of eta going to infinity, which is 1. So if you're interested in numerical methods, now you can implement this in a code, you can solve it, and you get the boundary layer profiles for pressure gradients. And if you're not so interested in numerical methods, you can just go on the home page, and there's actually a code there. It's not the Blasius.m. The Blasius.m only does Blasius, but I have added also a Jupyter notebook there, which you can look at. I will update it. I haven't updated it, but I will do that tonight, where you can also, which works for both Blasius and Faulkner-Scan. So if you want to try out a few profiles. Now, just as a kind of a final sentence here, so the Faulkner-Scan profiles for solutions, they are actually used. They're often used because they provide exact base flow solutions for pressure gradients. Why I'm writing here exact in quotes is, well, first of all, you need to calculate the profile still numerically as a solution of this ODE, but not only that, it's of course only solutions to the boundary layer equations. It's not to Navier-Stokes. It's only solutions to the boundary layer equations. But still, with that in mind, it's exact solutions that you can reproduce, and you have a good reference case for your works. Yeah, just for completeness, I would just like to draw again some of these profiles. So in the middle, we would have the Blasius profile, which would be the ZPG profile, and then you would have maybe the FPG profile here, the APG profile here. So the FPG would be kind of this fuller profile, as we were saying before, when the gradient is higher. And in this case, you would get something that may even look like this, where the gradient is such that the screen friction is lower, so something like that. Now, the last comment I would like to make here is that now, because we have actually calculated the profile, or we have not calculated it, but we have the equation for the profile. We can, of course, calculate all these things, thicknesses, delta 99, delta star, theta, and so on. But of course, we can also calculate h, this h12, the shape factor. And I was saying at the time, when we introduced h in the beginning of the lecture today, that h is actually a measure for the thickness of the profile, or in that sense also the actual pressure gradient. So we know now that h for the zero pressure gradient case was this 2.59. That's the Gaussian. Now, as I was saying, h is a measure for the thickness of the profile. Actually, it's a measure of the inverse thickness, because it turns out that for APG, you would actually get a higher value, and for FPGs, you would get a lower value. So, in a sense, so the thicker the profile is, the lower h is. In the extreme case, when you have a rectangular profile, h would be, what would h be in this case? 0. No, 1. So this would be h being 1. Because in the end, it's a ratio of two thicknesses. In this case, both thicknesses are the same. So that's why it becomes 1. So that means the thickest profile that is possible would be h being 1, and of course the thinnest profile would be h being 1. So h is something that goes from 1 to high values. And the thicker it is, the lower the value is. Maybe I should write that down quickly. So h12 is a measure for the, let's say, inverse thickness, or maybe the thinness, if you wish, of a profile. And the h12 is always larger or equal to 1. Okay, as I said, if you're interested in also looking at solutions of this, go on the homepage tonight, and then there will be this Python code which you can run and look at and calculate profiles. Okay, but with this, I would actually like to conclude for not for today, but for this part. I would like to stop talking about boundary layers and continue with stability. But before I do, I would like to ask whether there is any questions regarding this part about boundary layers, about calculations of Blasius, Faulkner scan, etc. Anything that is unclear or anything that we should maybe go through again?
I have a question.
Yes?
Regarding the example of, for example, Ivan's flow and the sync flow, what happened whether we change the frame of reference of the dx, for example, we invert the direction?
So, for instance, in the sync flow?
Yeah. What will we have to change?
So let's see. Let's see whether we can improvise this. So what you can do here, okay. So what you're saying is if x is like this, and you would now, so the sync flow was like that, you would like to have it like this, perhaps. Something like that?
Yeah.
Let's see whether. So let's see. Yeah. Exactly. Something like this, or maybe we can. Yeah. No, let's do like this. Something like this. Okay. So this is actually, it's good that you mentioned that, because this is another example which kind of, which can be used, which is something that's called the converging channel. It's not the sync flow, but it's a converging channel. Right here. And the basic idea, I guess, in such an example would be that, again, you would have, I guess this is still the same, that your UE would be 1 over x, would be 1 over h of x. That would still be the same. That's for the continuity. Now, I guess the question would be, or one question that you could ask here is, you know, in the end, you need to have something that you would like to you know, some shape or some condition that you would like to fulfill. In the sync flow, the example was easy because you say at x being 0, you're converging. That's why you know that h is x. Now, in this case, in the converging channel, one potential question could be that you say, well, I would like to have, so for instance, I would like to have m equals 1, for instance, which would mean that if we go to the equations, where do we have it? And so that your velocity profile would be kind of linearly increasing with that. That could be a potential question that you have. And then the resulting question then is what type of shape that you would get out from that. So in this case, what you could do is if you set that you would like to have m being, so this is again just for completeness, this is h of x, and I guess this would be your UE of x, something like that. And if now your question would be, so if you have m being 1, so that means that your h of x could be, in this case, maybe 1 over x, so that would be kind of the same, or the inverse of what we had here, because if you switch around, then of course we would exactly get this. UE would then be, you know, 1 over h, which would be x to the 1. Yeah, x to the 1, so with that m being 1. Right? So that is now a case where h would change like this. Then you would have UE to be linearly increasing with n. And of course, now comes the question, what would delta do in this particular case? And again, we know for delta that's proportional to x to the 1 minus m divided by 2. And in this case, when m is 1, well, then we would get x to the 0 to be, and then in the end we would have constant. So actually now I realize that maybe the actual question, maybe we should turn that around. That's probably more interesting. We should probably do it like this. That we say, actually the starting point would be, starting point would be like this. That we would say, I mean, one possible question would be, what would need to be the shape of the wall in order to have a constant boundary layer thickness, for instance? And then we could say, okay, then we have, obviously, this needs to be constant, so m needs to be 1. Sorry, I mean, I'm kind of improvising this. So we want the constant boundary layer thickness, then that means m is 1, and of course, if m is 1, UE is x, and that means that h is 1 over x, for instance. So you know now, if you want to have a constant boundary layer thickness, this would actually not be straight, it would kind of be something like that. I don't know whether this to some extent answers your question, but you can kind of, you can play around with that. It's always, of course, the question, what do you impose and what do you want to get out? Now in this case, perhaps I want to have a constant boundary layer thickness, give me the shape. Up here it was, I have the shape, give me the change of the boundary layer thickness. Okay. Any other question or comment? If not, then I actually would like to stop with this part, and now we really successfully stopped or finalized the part about boundary layers. So we have, in the beginning, we talked about viscous flows, exact solutions with vorticity and that stuff. Now we talked about boundary layers, and now the third topic that we will talk about is stability and transition. And actually, in order to do that, I would like to start with a few slides that I prepared. So I try to switch here into PowerPoint some way. So maybe I should stop sharing it first. So, okay, because I need to open the PowerPoint first. So, yeah. Okay, where's now the, where's the, so, okay, so I would like to start with a few slides on stability and kind of motivating why stability is actually an interesting topic. So let's start with this picture. Have you seen something like that before? I mean, it's a chimney. I guess you have seen a chimney. But have you seen this kind of spiral things on chimneys? No? Yeah? Have you seen this? An antenna with a spiral? Why?
Because of vibration.
And why would you get a vibration? What type of vibration would you get on that?
Because when you have flow around the cylindrical body, you will have the vorticity that will make it
exactly.
vibrate.
Exactly. What you get is you will get what is called a Kármán vortex street. So you get a regular shedding of vortices to the left, to the right, to the left, to the right, with a very specific frequency, which is related to the velocity of the flow and the thickness of the diameter, the radius of the obstacle. But what would now happen, or so why do you have these spirals? I mean, here on the chimney, it's kind of clear. For the car antenna, you can also see there is some, there is some spirals in there. What is now the purpose of these spirals?
Because this will cancel the vorticity, kind of.
Kind of. Essentially what they do, or what the spirals do, they break the coherency of the vortices. So you will not get kind of a coherent, everything goes to the left, everything goes to the right, which then would be quite strong forces on the structure, which then of course leads to either destruction of this thing, or maybe in a car you would really start to vibrate this antenna. If you have this spiral, it means that not everything goes to the same direction at the same time. That means, of course, that the forces are weaker and the deflections are weaker. But the reason why I'm showing you this is that at the very bottom of this problem is that there is an instability of the flow around the cylinder that creates this periodic pattern, and the spiral here is just to kill this instability, or not kill, to destroy the effect of it. So in the end, we're dealing here with a stability problem. So we need to understand the flow from a stability point of view to predict the appearance of these vortices. And then once we have understood that, once we know what the frequencies are, then we can start to affect it. But at the very bottom, this is actually a stability problem that you see here in these very large scales. So that's kind of one motivation, or one everyday motivation why stability is actually irrelevant. I mean, another kind of nice picture is for stability or transition is here. I mean, you see here the smoke that comes first. It's very kind of nice and straight. Then it starts to wiggle a little bit, and then of course at some point it's fully turned. So I guess this picture to some extent also explains a little bit what different stages we're actually looking at. We start with the laminar flow at first, you know, the kind of flows that we have looked at before, laminar, Poisson flow, pipe flow, and so on. At some point they become transitional. You can see here a typo, sorry. Transitional meaning that you have some instabilities that are growing, typically in a wave-like form, as we just discussed for the Kármán vortex street. So there's a regular wave, but at some point the amplitudes are so large that they become nonlinear, and then at some point it will break down to a chaotic flow at the very end. Now, coming a little bit back to this Kármán vortex street that we just talked about when it comes to the chimney, this is kind of the 2D visualization of the Kármán vortex street. So you have the flow coming in from this side, and then you have this periodic shedding of vorticity. And it's exactly this type of pattern that you would like to destroy with this line. And actually the cool thing is that this is now a laminar flow. It's maybe not so interesting, but actually you can see that also on a very, very large scale. So this is now a cloud pattern. There's a little island here, and there's a cloud pattern around that. So you see that this Kármán vortex street is, you know, on the orders of kilometers or tens of kilometers. And of course, the Reynolds number here is extremely high, very far away from this, you know, 47 in this case. It's probably a Reynolds number of millions, but yet you have the same large-scale picture, which again motivates why stability is actually important. You can also do that further in kind of 3D configurations. This is a recent simulation that we have done in Stockholm, where you can see, which is so-called stepped cylinder, where you have two different diameters, where you have kind of normal behavior out here, but then in the middle it's actually kind of cool because you have different frequencies meeting, and then there's some interesting stuff happening. So the Kármán vortex street, that's one of the, I would say, the 2 or 3 most famous instabilities. The other famous instability is this one here, which is called the Kelvin-Helmholtz instability. And it's essentially what we would call a shear layer instability, when you have two fluids that shear with respect to each other. And this is an interesting experiment where this instability is shown. So this guy here, he will now lift this instrument up, so it will kind of tilt. And it turns out that the red water, or the water with red dye, is a little bit heavier than the transparent one. So the red one, after it's tilted, would like to flow down, and the transparent one would like to flow up because of the buoyancy force. And of course, that gives you then this shearing at the interface. Let's now see what happens. So now he's working on it. So he's tilting it. So you can see that the red bit is starting to move down. And then at some point the shearing is just large enough to get these very nice vortices, these very nice structures exactly at the interface, but only for a short time. They grow exponentially fast, and then at some point they become fully turbulent. Now of course you see that again. So we have slow exponential growth, Now you see it. This very nice structure, this roll-up of vortices, but then very quickly it's become turbulent. But these type of structures you see all the time whenever you have two fluids shearing with each other. And of course, the kind of one example is this one here, where you have two layers of air shearing with each other. If you happen to have clouds right there, so a little bit of vapor, which kind of acts as a tracer, you can actually see these instabilities. So I'm sure you have seen these type of things. Of course, instabilities are also present in pipe flow. And I guess this is this famous experiment that was performed by Osborne Reynolds in 1883, so 150 years ago, or 40 years ago. So the idea here is that you have a pipe flow here. So here we have a pipe, and you can adjust the Reynolds number. Well, at the time it was not called the Reynolds number, obviously, but you can adjust the speed of how fast you have this this flow going. And then the Reynolds had this idea of injecting a little bit of dye, color, into this flow. And then he was seeing that as soon as the Reynolds number or the speed was higher than a certain threshold, it started to wiggle. So this is from his original paper from 1883. So in figure number, so the topmost, that was for a low Reynolds number, so you don't see anything, it's just a constant stream. And then for figure 4, that is kind of when you have reached the transitional Reynolds number, you see that there's kind of wiggles starting here, and then it becomes turbulent later on. And if you take a short exposure, so you essentially just take a picture, then you really see that it starts to wiggle. And this would be the onset of instability. And actually, there were some people that redid this experiment recently and also made a video. It's this one here. What happens here is that you slowly increase the flow rate while the video is going. And then, of course, at some point you see that you get small wiggles, and because you still increase the flow rate, so you increase the Reynolds number, these wiggles become larger and larger up to the point that the flow here at the end actually becomes fully turbulent. So stability theory is all about trying to explain, let's say, this state here, when you have the first time that you get a wave appearing, and we would like to understand what are the conditions that are needed for this wave to appear. And then transition, I guess, would be the state when they have reached nonlinear amplitudes. And then, of course, study of turbulent flow, that's what Ramis does in a week or so. That's then kind of the end of this. Yeah, I guess this we've seen, the Moody diagram in a sense. First laminar, then it becomes turbulent. And what we're now interested in is exactly this region, where we go away from the laminar correlation, we jump up to the turbulent one. And what we would like to understand here is, why does this happen, or under what conditions this actually is going to happen. Okay, the last example for kind of classical example of where transition or stability is relevant is this flow case, which is called the Rayleigh-Benard convection. I guess you've also heard about that before. The idea is you have a channel where you have a hot wall and a cold wall. The hot wall is below, the hot wall is in the hot wall is in the bottom, the cold wall is on top. So that means that the fluid is warmed up at the bottom. It's warmed up, so that means the density goes down, so it wants to go up, and the cold fluid wants to go down. So that means you have some sort of pressure that it wants to go up and down, but of course you also have viscosity that doesn't really want this to happen. But at some point, the buoyancy forces are so strong that they overcome the restitutive forces of the viscosity, and it actually starts to mix. And in 2D, this is kind of what would happen. You would again, at some point, you would see kind of a wavy pattern, but very quickly also that would become nonlinear. And now it's not really turbulent because this is a 2D case, but a chaotic mixing would start. So again, the instability question would be at this stage when you would answer the question whether you would get these wiggles or not. And of course, this is also something that of course happens in 3D and in reality. I guess you've all heard about these hexagonal, what is this? 1, 2, 3, 4, 5, 6. Yeah, hexagonal patterns of these convection cells. But you can actually also see that when you just look at foods, for instance. This is one of those Japanese soups where you still kind of have heating from below and cooling from the top surface. You can actually see these convection cells building up. They're not exactly in the same nice regular pattern, but you can kind of imagine that would, if you had a huge pot of soup, it would kind of be hexagonal. I have to say this is not exactly Rayleigh-Benard. This is a Maragoni convection because it's actually from you're not fixing the temperature, but rather the heat flux on top. But the principle is the same. Yeah, so these were a few examples of what or where instability is, of course, relevant. Now, being here at the kind of the Department of Aeronautics, of course, in airplanes, in cars, transition is, of course, important because you typically, well, no, I would not say you don't want it, but you need to know where transition happens in order to be able to design your wing or your surface in the best possible way. But of course, transition happens on any body, on wings, on car surfaces. And in the end, we need to understand how to predict where it happens. And of course, in order to build a model of transition, you need to understand what the physical principles behind transition are. Now, this is the last slide for today, but I guess it kind of illustrates a little bit what we also mean with stability and transition. So if you now first just talk about the concept of stability, I guess the basic idea is we would like to understand whether a state is stable or unstable. Stable means, that's illustrated in this situation here, it's just a ball in a kind of curved mole or something. So the idea is, if I kick this ball a little bit, it would, of course, go back and forth, but after a while it would actually stay in this, it will end up in the same position. So that means that is a stable situation. If I apply a small perturbation, it will actually go back to its original state. That's what we would call stability. Obviously, this situation here would be unstable. So maybe I managed to balance the sphere on top of this little hill, but as soon as I hit it a little bit, so I kick it here from the side, I would of course roll down on either side of this hill. It will never go back up. And this is what we would call an unstable system. And obviously, in between stable and unstable is kind of the neutral system, where I can push the ball, but then it would just go into the same position but somewhere else. So that's kind of in the middle of it. And then also very relevant for fluids problem is this fourth picture here. That is what we would call conditionally stable. That means it is stable, so I can kick the ball. It is stable up to a certain point. And if I kick the ball too hard, it will actually go over here into another situation. So it's not stable for any amplitude of perturbations. So I guess these are the four different states that we will consider now in the next few hours applied to fluids problems. And it actually turns out that all of them are relevant. There will be situations where the flow is completely stable. You can do whatever you want. It will go back to its original state. But there will be also situations when I can just hit them a little bit, but then at some point it will go to another state. So all of these things will be relevant in the considerations then starting tomorrow. So with this, I guess now we should wait for the beep. But I guess with this I would like to close for today. And tomorrow we will start with the theory on stability, which is my personal favorite topic. So it will be hopefully very interesting. I guess we see each other again at 3 o'clock in this room tomorrow. Okay, thank you very much.